Okay, so now I'm going to do something a little bit different. I'm going to get rid of this, and I'm going to get rid of this. And what we're going to do now is I'm going to introduce a method to numerically approximate integrals, and in the next video, a way to numerically approximate derivatives. So let's say we have, I'm just going to write this in Markdown here so you can see what I'm talking about. This obviously isn't going to be code. But let's say we want to do a function. Let's say we want to do the integral of a function, so it looks something like this: the integral from a to b of some function f of x dx. So let's say we want to do this integral. Remember that the Riemann sum definition, this isn't exactly the precise definition of Riemann sums, but it was something like this: the limit as delta x, now let me say h goes to 0, h goes to 0, and we're going to look at f of x k, and then we're going to multiply this times h. And remember what f of x k is. This is the limit h goes to 0, and I will run this in just a little bit so it doesn't look like computer code. This is a plus k times h times h. So this, the way that I've set it up here, this would correspond to like a left-hand endpoint rule. And then, oh, sorry, I forgot the sum. K equals 1 to n, and here n is a number of intervals. Probably some of you guys were screaming at the computer screen. K equals 1. Actually, I guess now the way that I've set this up, this would be like the right-hand endpoint rule. At any rate, when I run this, this is the definition of Riemann sum, and I guess h and n are connected. So however you want to think about it, h is equal to b minus a over n. So we can either think about this as being the limit as n goes to infinity. N again is the number of subintervals. We're dividing it into equally spaced subintervals. We can define this like this: either as n goes to infinity or as h goes to 0. Okay, so f of xk would be like the height of the rectangle, and h is the width, so this is the area of the rectangle. Okay, now what happens as n goes to infinity, this sum is going to be a better approximation to the integral, and we define the integral to be equal to whatever this limit is, as long as a limit exists. And that's what we're going to be assuming for this class. So what I want to do now is introduce a way where we can think about a very basic way to implement this numerically. So what we're going to do then, we're going to use NumPy to compute these Riemann sums for a finite n, and then do that for, as n gets bigger and bigger and bigger, and stop when it meets some tolerance, when it gets to be precise enough, which I'll define in just a moment. But for now, let's just say n is equal to 10, and let's say we have a function. Actually, let me do it like this. Let's say we have a function that we want to integrate. Let's just say we want to integrate x squared because we know what that integral should be. And let's say we want to integrate from a equals 0 to b is equal to 1. Of course, we'll play around with all of this stuff later on. So if I integrate x squared from 0 to 1, I guess the answer there should be 1/3, because the antiderivative of x squared is x cubed over 3. We're going from 0 to 1, should be 1/3. And let's say I'm going to approximate with just 2 subintervals. And now what I want is I want to create an array that has 2 subintervals. I want to create an array going from a to b that has 2 subintervals. So to do that, oh, I thought I had it up here. We're going to use linspace. So linspace is like arange in that it gives us a NumPy array. Only here we give it a starting value, which for us would be a. We give it a stopping value, which for us would be equal to b, and we give it a number of subintervals, which in this case, or a number of intervals, which in this case would be 2, would be n. So let's just look at this really quickly. So I'm going to call this the x values. This is equal to np.linspace. Let's just check this out to see what we get when we put in a, b, and n. This is just me kind of playing around with inspace. So that you can kind of see what's going on. So if I run this, we're going to get array with 0 and 1. Okay, so the first element of the array is 0, and the second element of the array is 1. Now that's not maybe exactly what we want, because we want to think about if there are two subintervals, we should think about there being one interval going from 0 to 1/2 and one interval going from 1/2 to 1. And so the numbers here in the array are kind of like the endpoints of those intervals. Okay, so we've got 0, 1/2, what we would expect to have, but that's not what we have. So here's one of the things. There's a number of ways to fix this. I think the best way to fix it is to come over here. This says endpoint equals true. If we come down, if true, stop is the last sample. Otherwise, it is not included. So this is kind of like with A range. When we went from A to B, that last endpoint was never included. If we do like this and say endpoint equals false, we're going to get something that's a little closer to what we needed to be. So 0 to 0.5. And if we think about what we should get when we have 3, we would want there to be 0, 1/3, and 2/3, which is exactly what we get here. Okay, so now what we have is this is going to be x_vals is now going to be a set of x values. These are the sample points. And what we're going to do is we're going to evaluate the function at each one of those sample points. Okay, that corresponds to this f of xk. We're going to multiply by the width of the width of the rectangles, which is just the distance between each point, which is going to be our h value, and then we're going to add them all up. So now h is going to be equal. So there's a number of ways that we can do this. There's a number of ways we could do this. One way would be to do x_vals of 0. Of 1 minus x_vals 0, and we're going to get, not going to get anything if I don't do the code right. We're going to get 1/3, but really I think the best way to think about this is b minus a over n, and we're going to get 1/3 that way. So this is b minus a over n. And so what we're doing, we're going to add up, we're going to evaluate f at each one of these points. So when I say f, I mean our function here. So we're going to evaluate this. It's going to be f of x_val. So let me run this. I need to put fun. So the reason it has this about my fun is because remember in a previous video I said f is equal to complex numbers.myfun. So I need to do this. Okay. So now everything is set up. So now what y values is, if we print y values, this is just going to be f evaluated at each of the endpoints. So 0 squared is 0, 0.3 squared is 0.1111, and this is 0.67 squared. And we can actually plot this, plt.plot, just to make sure that we've done everything correctly. So this is just kind of part of code testing. This looks like, well, it doesn't exactly look like x squared, but it looks kind of like x squared. If we have even more points, let's just say 50 to make sure we've done everything correctly. We should get something here that looks like x squared, the graph of y equals x squared, and that is indeed what we get. But I'm going to put this back to 2 now. Okay. All of this was just to test, to make sure that x values is what I thought it is going. X values is what I think it's going to be. Why would it not be? Well, the first time I did this, I had endpoint equals true, or I just didn't. If you come here, it says that the default is endpoint is equal to true, and that didn't give me what I wanted. And so I'm constantly testing things to make sure they behave the way that I want them to do. Of course, once you get experience, you won't have to test it as much. You'll be more confident in the way things work. Okay, so now this sum right here, all it is the sum of y values, the sum of every element in y values times h. That's equivalent. All right, the h doesn't depend on k, so you can move the h outside of the sum there. Okay, so now what I'm going to do is I'm going to say the integral. So I'm going to say, I don't want to use int because that looks like integer. I'm just going to say integral is equal. It's going to be equal to h times h times x vals the sum. So x vals dot sum, or sorry, not x vals, y vals. Y vals dot sum. So now print integral. This is going to be the approximation to the integral Okay, we get 0.125. Now we know the answer should be 0.3. This is still a little bit far off. Let's see what happens if I do this with n is equal to 5. Getting a little closer. Let's see, n is equal to 10. We've got this. Let's just bump it up to, let's do 50. Okay, getting closer. Let's do 100. Okay, and we can see as we do this more and more times, we're going to get something that's getting closer and closer to 1/3. Though honestly, this is not converging as fast as I thought it would be. But again, we're doing a very naive approximation here, just using Riemann sums. Okay, so at any rate, I hope, if it's not completely clear now, maybe if you think a little bit further what's going on, this will give the Riemann sum for n equal to 1,000. I guess it's 10,000 here, already all the way up to 100,000. Whatever n is, this is going to give the Riemann sum for the function, whatever we have here, going from 0 to 1. So for example, if I change this to x, I know that if I integrate x from 0 to 1, the answer is 1/2. So I should get something pretty close to 1/2. And of course I do here, get something close to 1/2. Okay, so a question, there's two things that we need to consider here. The first one is kind of the mathematical one, and the second one is kind of a more of a programming thing. The mathematical one is, when I did this, I started at 2, and I ran it, and it was 0.25. Then I looked at 10, and I ran it, and it was that, and then 100, and I can run it again, and it gets to 0.49, and 1,000, I run it again, it gets to 0.4995. Now, of course, I know that the answer is 0.5, but let's forget that I know the answer should be 0.5. The question is, if I want to automate this, that is, if I want some automated way for picking more, higher and higher values of n, how do I know when to stop? In other words, how do I know my precision is enough and I don't need to go on anymore? Obviously, part of that is going to be based on how precise my answer needs to be. But if I know the answer is 0.5, then I can always just do this until this is within whatever tolerance of 0.5. On the other hand, that doesn't really make a whole lot of sense, because if I know the answer is 0.5, then I will just use the answer as 0.5. So the idea is that we're going to use, let's say this number up here. Let's say we define something like a sequence where Sn is going to be equal to this sum right here. Now, by definition, if the integral exists, Sn is going to converge to some number. So Sn is a sequence that converges. Convergent sequences are Cauchy sequences, meaning that as n goes to infinity, not only is Sn going to go to some number, but successive values like Sn and Sn plus 1, that difference is going to go to 0 as n goes to infinity. So let me just say this more explicitly, or type this. So the limit as n goes to infinity, of Sn plus 1 minus Sn, this is equal to 0. So in other words, what we're going to do is we're going to pick more and more values of n. We're going to pick higher and higher values of n until the difference between the n and the n plus 1th iteration or estimate is below some certain threshold, and then we can be confident that then we can be somewhat confident that Sn is going to be pretty close to the value of the integral. Now, that might not be true. You could have some crazy sequence where there's a whole bunch of terms that start out really, really close together, and then they get farther and farther apart, and then get closer back together. But we're going to assume that on reasonable functions, things like that doesn't happen. Things like that won't happen. So basically, then what we need to do is we need to make a loop out of this. So I'm going to say tolerance. I'm going to set my tolerance equal to 0.01. And I'm going to say that instead of Sn and Sn plus 1, I'm going to call it current S. Current S is going to be equal, so I'm going to set n is equal to 2. Sorry. Let me get rid of this. Okay, n is equal to 2, and I'm going to say the current value of s, that is the current value of the integral. So I'm going to do current s is equal to, good gosh, sorry, I'm having problems here. So I'm gonna start off basically the first loop of the iteration I'm going to have outside of the integral, or I'm sorry, outside of the explicit loop. Okay, and so I'm going to say current s is equal to this right here. Sorry, this is the current value of s. I'm just going to get rid of this now because it's confusing me having that there. So h, actually all I'm doing is I'm retyping what I had before, just using this language of current s, b minus a divided by n. Okay, current s is equal to that, and tolerance is equal to 0.01, and then difference, I'm just going to say difference. The difference is going to be between the current s and the next s. So because I want to do the loop, I'm going to say difference is equal to 2 times tolerance, just to make sure that I'm bigger than tolerance. And I'm going to say while, and there's different ways of setting this up, while difference is greater than tolerance, okay, n is equal to 2 times n. So I'm going to multiply n by 2. But instead of saying n is equal to 2 times n, I'm going to say n times equals 2. So this, remember, means saying n is now going to be equal to n times 2. And then I'm going to say that s, so that's the next s, s is going to be equal, y values. So there's a number of ways to combine this into one line of code as well. I'm not going to do that though. X values is equal to np dot linspace a b n endpoint equals false. Y values is equal to fun of x values, and then s is going to be equal to the approximation of the integral. So it'll be y, or sorry, let me do h first. H is equal to b minus a over n, and now s is going to be equal to y vals dot sum, and I'm going to multiply this by h. Let me multiply it over here. Okay. Now I'm going to compute diff. So diff is equal to current s, np.absolute current s minus s. Let me do a capital letter there because I had a capital letter like that. Okay, and now I'm going to set current s to now this s. So current s is now equal to s. Okay, so I'm going to set my tolerance to 0.1 now, just because I want to see what happens. And then what we're going to print out is we're going to print s. So once the difference in successive things drops below 0.1, we're going to drop to s. And actually, what I want to do is I want to kind of track this as I'm testing. So I'm going to have it print whatever the current value is. So I'm going to run this now. 0.25, 0.375, 0.3475. So if we do something like 0.4375 minus 0.375, and we run this, we get 0.0625, which is indeed less than 0.1, but the difference there is not less than 0.1. If we do 0.375 minus 0.25 and run this, okay, it's 0.125. Okay, well now let me do up to 0.01 and see what we get if I run this. Okay, and then I can make this 0.001 or whatever I did there, and we get all the way up to this, and so on and so forth. Okay, and so now the point is that we can rest assured that this sum is more or less between that the real answer is plus or minus the tolerance. This is essentially the idea that we have here. Okay, now the part that the other issue that we have is, remember, we're going to be calling this function on an array. So really what we need to do is we need to have a vectorized version of this function. So instead of doing fun of absolute values, we need to make a vectorized version and do vfun of absolute value, vfun of the x values. For this problem, for this function, everything worked out well. But if I had like an if statement, if my function was piecewise defined here, I would need to have, this wouldn't work, okay? So then I'm going to say vfun is equal to np dot vectorize function. And now when I run this, everything should work out. We get the same exact answer. So remember, the reason that we need to do that differently is because we could say something like this. If x is less than 0 or x is greater than 10, return 0. And then otherwise, we're going to return x. So this would mean something like x is going to be 0. This function is going to be 0 for x going from minus infinity to 0. And it's going to be 0 after 10. But from 0 to 10, f of x is just going to be equal to x. That's what this says. Okay. If I were to keep this down here as function, so I'm going to back up and show you what would happen if we didn't do this vectorization. There's going to be that error message that we saw below that says the truth value of an array is ambiguous. Okay, the truth value of an array with more than one element is ambiguous. However, if we use this vfun, Python vectorizes this for us, or NumPy vectorizes this for us, and we should get something that works exactly as expected, and we do. Okay, I'm going to say one more thing that I want to say. Part of the project is you are going to write a class where all of this stuff right here, basically all of this stuff right here, instead of printing s, you'll be returning s. All of this stuff right here is going to be within a method in a class. So you're just going to put this, basically almost copy and paste this code into the method in the class definition that I've given you, or that I will give you for the project. Okay, sorry, I realize this was a long video. We're just doing numerical integration. I hope it makes sense. If not, as always, let me know.